Strong acids and strong and weak acids and bases. So we're talking about strong acids, weak acids, strong bases, weak bases. So strong acids. These are the same. This is the same idea as a strong electrolyte. A strong acid is one that completely ionizes in solution, and weak acids do not completely ionize. When we look at the formulas here, HF and HCl, they look pretty similar. Okay, they're binary acids, and the elements fluorine and chlorine are in the same group in the periodic table. They're even right next to each other. And so we think, well, these guys are really, really similar. And they're similar in some ways, and yet in other ways they are not. HCl is a strong acid. HF is a weak acid. When we put hydrochloric acid in solution, it ionizes completely. And now here we are showing you what actually is happening, where the proton, the hydrogen ion that's coming from this acid, does not hang around by itself in solution. It rides piggyback on water molecules and forms that hydronium ion. And then we have chloride ions. But we have no HCl molecules in here. And here's the space-filling models. We don't have any of these guys present in solution. They all come apart. And that's what makes it a strong acid. Strong acids are strong electrolytes. When we did the conductivity demonstration in lab, we did HCl. And HCl made the light bulb burn very brightly. It's a strong acid, it's a strong electrolyte. The other thing we can know about them in terms of concentrations is if we have a 1 molar HCl solution, that's 1 mole per liter HCl. For every mole of HCl, we're going to have a mole of hydronium ions. And so the concentration of hydronium ions will be the same as the concentration of the acid, because it's a one-for-one thing. You can think of this as a pair of shoes. There's the left shoe and the right shoe. If you have 100 pairs of shoes and you separate them all, how many left shoes do you have? 100, right? They came in together. They're perfectly matched up. When we see this bracket, and we've already been exposed to this because we did chapter 15 ahead of time. But when we have a formula inside the brackets, it just means the molar concentration of whatever that is. So this is the concentration of hydronium ion, in molarity, moles per liter. So when we put hydrogen chloride, hydrochloric acid in water, this reaction occurs. This is a single arrow, which is indicating that it goes to completion. So we have hydronium ions, we have chloride ions, and that's it. That's a strong acid. Here's pictures of a demonstration similar to what we did. Here's water, pure water. Doesn't conduct electricity. There are no charged species in pure water. Now, remember we did the tap water and that glowed a little bit, right? Because there's dissolved stuff in your tap water. And that's not necessarily a bad thing. But pure water will not conduct. But you put some hydrochloric acid in there and now the light bulb goes on. Because the hydrochloric acid ionizes, forms lots of charged particles which can carry the electric current. There are, according to your book, 6 strong acids. I learned that there were 7, but now I can't remember what the other one is, so I guess that's kind of a moot point. These are the 6 strong acids, and you may want to include those on your note card for the final. Hydrochloric acid, hydrobromic acid, hydroiodic acid. So these are binary halo acids. But hydrogen fluoride is not a strong acid, but the chlorine, bromine, iodine ones are. And then we've got these, oh, I know what's, no, never mind, I don't. Okay, sorry. Nitric acid, perchloric acid, sulfuric acid. These are also strong acids. When we talk about a monoprotic acid, we mean an acid like HCl or HNO3 or HClO4 that has one ionizable hydrogen. Sulfuric acid is an example of a diprotic acid. It has two ionizable hydrogens. And all the ionizable hydrogens will be listed at the beginning of the formula, always. So H2SO4, it contains two ionizable hydrogen ions or protons. Weak acids do not ionize completely. They actually form very few ions. So here's HF. When you put hydrofluoric acid in water, it's in equilibrium, and it actually lies far to the left. It does form some hydronium ions and some fluoride ions, but only a few. It does not ionize completely, and these are poor conductors of electricity. Here's the picture. We put the HF in water. It does form some hydrogen ions, but we also have a lot of intact molecules hanging around. And here in the picture we see we've got lots of the molecules and only a few ions. So strong acid completely ionizes. All you have are ions. Weak acid only does it a little bit because it's weak. So comparing the water and a solution of HF, and we see this is just barely glowing. So there are some ions, but not nearly as many. Here are some common weak acids: hydrofluoric acid, acetic acid, formic acid. That's what ants, those nasty California fire ants, inject into your skin when they bite you. That's why it stings so bad. They're putting formic acid in your skin. Sulfurous, carbonic, phosphoric. The way we usually think of this is we learn or make a note of the strong acids, and anything that's not on the list is a weak acid. So these are just some examples. Two of these are diprotic. Can you find them? Well, yeah, I guess they're kind of labeled there, aren't they? That was a really dumb question. And this one's triprotic, just H3. We'll just go on now. Okay, looking at pictures, A, B, or C, which one is a weak acid? Do we know what we're looking for? We're looking for ions and molecules. And they're labeled here for us. It takes a while to realize what you're looking at. So this has iodide ions and hydronium ions. And this solution has hydronium ions and nitrate ions. And this solution has three different things in it, right? These two are ions, and this is the molecule. So this guy is the weak acid because it did not completely ionize. So we're asked here to determine the hydronium ion concentration in each of these solutions. The first thing we need to figure out is this a strong acid? If it's a strong acid, we know that the hydronium ion concentration will be related to the actual concentration of the acid. Do you think that one's a strong acid? It's not. It's a weak acid. So do we know, with the information given, how much it ionizes? We don't. So the best we can do is to say that the hydronium ion concentration is less than 0.50. Because most of this stays as, lost my pointer, most of this stays as the molecule. So the ions are going to be less.
Okay.
Yes?
I'm sorry, I just didn't understand what you're talking about when you say it's less than. How do you know H3O is less than 0.5?
Okay, well, this will ionize. It's an acid. HCHO2. So it will ionize and form hydrogen ions and these formate ions. If this was a strong acid, that's a 2, not a question mark. If this was a strong acid, it would all go to ions. And from every one of these, we would form one hydrogen ion. But this is a weak acid, meaning most of it is still as molecules. So this 0.5 moles per liter means 0.5 moles of this stuff was put into a liter of water. Doesn't really say what happens to it after you put it in there. What happens to it is that some of it ionizes, but not all. So there are some hydrogen ions, but their concentration is going to be less than the concentration of this. Does that help?
Yes.
Because it's a weak acid. So let's look at HI, hydroiodic acid. Is that a strong acid or a weak acid?
Strong.
That's a strong acid. And so that goes completely to ions. So if we start out with 1.25 moles per liter of hydrogen iodide and it completely ionizes, then we must have 1.25 moles per liter of the hydrogen ion and 1.25 moles per liter of the iodide, right? You've got 100 shoes and they all get mixed up, they get unpaired. Then you have 100 of the left shoe and 100 of the right shoe. So it's not like we're doubling anything or making stuff come out of nowhere. It's just we've taken something and separated it. So you get more pieces that way. So the answer to this one is the 1.25. How about this one? 0.75 molar HF. It's going to be less than 0.75. Why? Because it's a weak acid. It's a weak acid, just like our first example. It ionizes partially. There are ways using ionization constants and other kinds of stuff that you can calculate that, but we save that for Chem 2. So this is as far as we're going to go with that. Strong bases, we're using the word strong in the same way. Strong bases dissociate or ionize completely. You'll notice that these are all metal hydroxides, these strong bases. Lithium, sodium, potassium, these are strong bases. They will ionize completely. So sodium hydroxide is a strong base. You put it in water, it ionizes completely. The molecule, you put it in, it comes apart. Weak bases, like the weak acids, do not ionize completely. Most of the weak bases produce hydroxide ions not because that's one of the ions in their formula, but because they're accepting a proton from the water, and that results in the water becoming hydroxide ions. So here's kind of a generic equation. We're saying this B stands for some weak base. The weak base accepts a proton from the water, becoming BH+, and that leaves the water as the hydroxide. This is an equilibrium, and it does not go to completion. So ammonia is probably the most common weak base that we see in this class, NH3. That is not necessarily easy to identify as a base, right? NaOH, KOH, we see the OH and we think, base, there we go. But this is a weak base. It accepts a hydrogen from water, so it does produce hydroxide ions in solution, but not just by ionizing. Question?
So, for the equations, the weak ones are going to have equilibrium versus
Yeah.
completion?
Yeah, so this equilibrium arrow is what tells us this does not go to completion. Now, previously, we sometimes get kind of sloppy with our arrows, and these are actually, like on the computer, these are a real pain. fact, I was looking for one this morning, and I know it's in there somewhere. I could not find it for anything. So sometimes when we're not concerned with, like if we're just doing stoichiometry or something, we tend to just always write a regular arrow. But when we are concerned, then we get specific, and we would include a double-headed arrow for an equilibrium, like this one, and then, come on, let me draw. So for a strong base, like sodium hydroxide, we would just put an arrow like this because it'll go to sodium ions and hydroxide ions. So here's the ammonia. You put ammonia in water. It will accept hydrogen ions from some water molecules, but it doesn't do that completely. And so we see here that we have a significant number of ammonia molecules that are intact. And that's the characteristic of a weak base. Same idea as a weak acid. Lots and lots of weak bases. So I guess if you're trying to guess on an exam, you're asked to say, well, is this a strong base or a weak base? Is this a strong acid or a weak acid? The number of strong acids and strong bases is much smaller than the number of weak bases and weak acids. Most acids and bases are weak. Only a few are strong. So I guess that could be a strategy. Just guess weak, right? It's not cheating. It's hedging your bets, right?
Mrs. King,
Yes.
but the double arrow also means partial ionization, correct? So if you automatically see a double arrow, doesn't it mean that it's weak? Because it's a partial?
Yeah.
I mean, instead of guessing like you're saying, that's a better.
No, but what if they don't give you an equation?
Okay.
What if they say HF?
All right.
What is it?
Weak acid.
Weak acid. And it is a weak acid. You definitely should be able to recognize it as an acid, because we learned that a long time ago. The names of acids have the word acid in them, right? That's always nice. And the formulas always start with H. So if it starts with H, it's an acid. And then if you're just, reduced to guessing, which guessing is better than leaving answers blank. Because if you don't answer the question, you have a 100% chance of getting it wrong, right? And if you guess, even wildly, you probably have a 20% chance of getting it correct. So that's better, right? So these are examples of some weak bases. And we see that when they react with water, we definitely do have this double-headed arrow. This is an equilibrium, meaning we've got this reaction going both ways. And generally it assumes that we have a significant concentration of reactants and products. But again, that all depends on the equilibrium constant. Okay, so here's a similar question to the one that we had about the acids. Barium hydroxide, strong base or weak base? Let's go back and look at that table. With the bases, oops. The strong bases all had something in common. They were metal hydroxides. Okay? So we get to this one and we look at this barium hydroxide. That's a strong base. How does this ionize? Completely. And what does it form? We get barium ion. And how many hydroxides? 2. So this molecule is not like a pair of shoes. This is more like I don't know, a bicycle, where you have a frame and two wheels. And when you take it apart, you have twice as many wheels as bicycles to start out with. And so that's something you kind of have to watch out for. So is the concentration of hydroxide ion equal to the concentration of barium hydroxide? No, it's twice as much, right? Because each one of these separates into two of those. Times 2. Do not trust my head. I think it's that 0.11. Yeah, it is 0.110 molar is equal to the hydroxide ion concentration. There's different ways of thinking about something like that. I mean, you can think of it in terms of dimensional analysis and converting units and stuff. And some people, that makes a lot of sense too, and that's great. And some of you, I know, are looking at me like, what? What? That other one was, we were just barely okay with that, and now you're pulling this times 2 on us. Look at the formula. Think about what's going on here. Okay, there's barium and 2. Do you see the shrink wrap here and the 2 on the outside? There's 2 hydroxides on it, right? And so what happens when you take it apart? You have twice as many hydroxides as the unit that you started with. There's got to be something better than bicycles. I'm just not really coming up with anything. But you take you have 5 bicycles, you take them apart, how many wheels do you have? 10. Well, how do you know that? Because it makes sense to you. You can imagine that. Close your eyes and imagine it. 5 bicycles and you take the wheels off. There's twice as many, right? This is the same idea. Okay? It's exactly the same. So it's not complicated math. It's just we need to get this visual picture of what all these crazy letters and numbers mean. And hopefully by the end of the semester now, you're at least on the verge of getting that picture and seeing, oh, that's what that is. Okay? Once you can see those sorts of things, a lot of these problems become much simpler. We're not having to remember some process to solve a problem. We can just think about it. Well, what would happen? Okay, that's a strong base. That means it comes apart into ions. We've got barium ions and 2 hydroxide ions. I'm going to get twice as many hydroxide ions as these units that I started with. So I don't know if that helps or not. Let's go on. Letter B. Less than 1.05. So we look at that, and we can't write while we're talking. We look at this, not a metal hydroxide, right? All the strong bases that were listed were metal hydroxides. This is going to be a weak base. Does not ionize completely, and so the concentration of hydroxide ions that it forms will be less than the concentration. That's all we can say with this information. How about letter C? It'll be 0.45. Because this one is more like the pair of shoes, right? 1 sodium, 1 hydroxide. And when you take those apart, you have the same number of each. Any questions?